Okay, hi, good morning, everybody. So how's your preparation for test number 3 going? Do you feel ready for tomorrow? Which is kind of a silly question because nobody will admit that they are ready for the exam. Oh, good, Fatuma. Kinda. Okay. Yeah, that's good to know. But yeah, if you have some questions about topics covered in the exam, just let me know in the chat because I look at the textbook and if I will assume that you finish section 9.2 today, there's just a little amount of problems that we can answer right now. I mean, the problems are not that interesting yet. The thing is, there's a lot of theoretical things that you have learned, probably definition of terms about sequences and so on, convergence, boundedness, least upper bound, greatest lower bound, and so on. But from a problem-solving point of view, there's still just a few interesting problems from those sections. So I think we can still defer starting section 9 or chapter 9 to Monday. But is that right? Did you finish 9.2 today?
Just said we finished 9.1 today.
Okay, that's even shorter than what I thought because that only covered the introduction about sequences, limits of sequences, and so on. I think boundedness is also there, but anyway, we can start talking about that on Monday. So we can devote all of today's meeting by to answering some of your questions. So let me know. I have a couple here from Fatuma. If you still have some questions, let me know. Even if you are starting to answer some quizzes about Section 9, I can also help you with those towards the end of the session. All right. Okay, so let me start. Okay. Right. So let me see. Okay, here we go. Problem. So let's do problem 5. So this is a worksheet 12, which is something we used, I guess, a couple of days ago, which contains some of the questions he sent in preparation for the test. So I'll just be appending our today's notes to that worksheet. So I'll let you know later in the post. Yeah, but I will again upload this as worksheet 12. Okay, first question, integral of 3 over x squared root of 16 plus x squared dx. Any particular difficulty with this one, Fatuma? Because I assume that you already know where to begin with this. If you look at the integrand, it involves a radical. And remember what we do with that situation, we do trig substitution, right? So whenever you have a radical of either of the form a squared minus x squared, or x squared minus a squared, or root of x squared plus a squared, chances are you can use trigonometric substitution, right? And that's what we have here. This is of the form x squared plus a squared. So we can use trigonometric substitution to get rid of the radical. So for that, we will let x be equal to 4 tangent theta, okay? But remember, whenever changing the variable in your integral, you should change it all the way. I mean, change the variables and change the differential as well. So to find appropriate differential replacement for dx, we take the derivative of 4 tangent theta. So that will give us 4 secant squared theta d theta. All right, and then let's plug this into our integral and pray that what we'll get is much simpler than the original integral. So you'll got the 3 here over x squared. So replace it by 4 tangent theta quantity squared. plus root of 16 plus 4 tangent theta squared. It seems that we're making the integral a lot complicated here, but this is we do this in order to get rid of the radical. So we are sort of sacrificing the algebraic form of the problem and turning it into a trigonometric function to the end of getting rid of the radical. So there should be no plus there. Okay. And how do we get rid of the radical? By letting x equals 4 tangent theta. You will see here that I can appeal to the Pythagorean theorem or the Pythagorean identity from trig. So what I'll do here is, okay, I'll just write it this way, okay, over 16 tangent squared theta. Now we'll have a 16 plus 16 tangent squared theta over here, d theta. You can skip some of the steps in the solution. I'm showing you all of the steps, but if you're already used to this technique, you might know some shortcut by say what happens to this guy after everything is done, then that's fine. I am just showing all the parts of the solution so that you will remember what happened in all of those steps, right? Okay, now I can work this out. So cancel 4s from them. So I'll get 3 over 4 outside. And we'll have secant squared theta over tangent squared theta. And here in the radical, I can factor out the 16 and be left with 1 minus tangent squared theta, d theta. All right. And I'll have 3/4 integral of secant squared theta all over. I'll have a tangent squared theta here. But this 16 that we factored out already is a perfect square. It can come out of the integral of the radical as a 4. And then we'll have the radical, the root of 1 plus tangent squared theta. And here's where we will see how we get rid of the radical. Note that using the Pythagorean identity, I have a 4. Hold on, let me put that as a 16 outside, right? I'll put this 4 outside of the radical. And then here, if you remember your trigonometry, 1 plus tangent squared theta is equal to secant squared theta. And here we will see how the radical will vanish, because here you have a perfect square, and yet you have it inside the radical, so they will cancel each other out, leaving us with 3 over 16 secant squared theta over tangent squared theta times simply secant theta d theta, putting the assumption that secant theta is positive. All right. And then I can cancel the secant in the denominator by one of the secants above. So we'll have 3 over 16 integral of secant theta over tangent squared theta d theta. All right. So the thing here is, how do we solve this? Well, you can try U substitution. The nice candidate for U substitution is from the denominator, right? Remember, that's our first go-to choice. Try the denominator first. But if we select U to be equal to tangent theta, we will need a secant squared theta d theta from the numerator to get the du. But unfortunately, we don't have a secant squared. We only have a secant theta left. So that means U substitution won't work. And if you recall all of the techniques that you learned in chapter 8, there is nothing that allows us to integrate something of this form, right? So whenever those methods fail, we go back to the basics. I mean, let's try to play with more trigonometric identities and try to write everything in terms of sines and cosines, right? So secant theta is 1 over cosine theta, while tangent squared is sine squared theta over cosine squared theta. And then you see that the cosine or one of the cosines will be canceled. Or, I mean, if you want some more details, you can write it as 1 over cosine theta times cosine squared theta over sine squared theta, d theta. And now it's apparent that we will get this over sine squared theta d theta. Okay? And at this point, I can let u to be equal to sine theta, because that will only cost me a cosine theta d theta to get the du. All right? So I'll have a 3 over 16 here. Cosine theta d theta is replaced by a du, and I'll have a u squared below. So this is just 3 over 16 times u to the minus 1 over negative 1 plus the arbitrary constant c. Remember that u squared in the denominator can be written as u to the minus 2. Use the power rule for integrals. You're going to get u to the minus 1 over minus 1. Okay? Or you can rewrite it as minus 3 over 16u plus c. And then we revert to the theta variable. U is sine theta plus c. Or I can say, oh, this is minus 3 over 16 of cosecant theta plus c. But we are not done yet because our answer right now is in terms of theta, but the original problem was given in terms of x. So to retrieve the antiderivative in terms of the variable x, we go back to our u substitution. Remember, we let x be equal to what again? It's 4 tangent theta. Or in other words, we let x over 4 be equal to tangent theta. Recalling SOHCAHTOA from high school, tangent is opposite over adjacent. So if you draw a triangle, let's assume that the right angle is here, then theta is here, then opposite theta should be x units. So opposite theta, so this is x units. And then adjacent to theta should be 4 units. And the hypotenuse using the Pythagorean theorem is x squared plus 16. And you know that you are on the right track if one of the legs of the triangle has measure equal to one of the radicals, right? So the leg here, or the hypotenuse here, happens to be square root of x squared plus 16, which is actually the expression that gave us problems in the first place. So you should be able to see that radical in the triangle in some form or the other, right? So now let's compute for cosecant theta. Well, cosecant theta from your SOHCAHTOA, it's the reciprocal of sine, so it should be hypotenuse over opposite. So hypotenuse is root of x squared plus 16, and opposite theta is x units. So basically, our final answer should be minus 3 over 16 of root of x squared plus 16 all over x plus the arbitrary constant c. Okay, is that good?
Yes, thank you. Also, I have a question.
Mhm.
Or like, I know we only have one FRQ question on the exam, but do I have to can I skip steps in between, or like will I get points off if I skip steps?
Well, it actually depends on what steps you skip. So if those steps are just merely manipulating constants and so on, you can skip that as long as you can do them on your head. So that's fine. But if it's a major step, then you should put it in there just to remove the possibility of the grader thinking that you copied it from somewhere else, because that's one added difficulty of having exams at home. So people have, or graders have the propensity, or a higher propensity to think that, oh, probably he or she copied it from somewhere else. So yeah, just to avoid those stuff, then I suggest make your solutions as detailed as possible, but you can skip some of the minute steps. Like for instance, here, definitely you can skip this step, for instance, oops, and come up with this one right away. Because all that happened there were arithmetic operations or some very, very mundane algebraic and trigonometric steps. But the main step, don't forget to write your use substitution thing. Make sure you include the first step wherein you just replace all the variables by the trigonometric function. You can skip some of these two lines. And then actually from here, I think you can go directly here. Because we already know what will happen to the root of 1 plus tangent squared theta. So you know that it will just reduce to secant theta. But it doesn't hurt to include some of the details. And actually, the more details you put in the solution, the higher the chance that you get partial credits if you didn't get the entire solution correctly. So yeah. I hope that answers your question. Mundane or simple steps actually is subjective in nature, but I'll say if these are basic algebraic or trig manipulations, then you're good.
Okay, thank you.
Jocelyn, good question. Inverse trig for going back to x. Well, that will happen if your integral, for instance, you solve a certain problem, all right? And then you come up with theta plus sine theta plus c. This is your answer, for instance, right? And then if you draw the triangle, say you have x here, you have 4 here, and then you have 16 plus x squared over here, we don't have a problem with sine theta. So say we have x over 4 is, oops, what was the substitution here? X equals 4 tangent theta. Okay. Now we don't have a problem with sine. That's the same principle as what we used before. So it's going to be x over root of 16 plus x squared plus c. But for the theta, we don't have any choice but to use trig function, inverse trig functions. So you go back here in this statement. So you divide both sides by 4. Now, to know what the value of theta is, the only resort that we can go to here is to take the arctan of both sides. So you take arctan here. So, and then this would be theta, right? That's the only way that you can get theta out of the tangent, to take the inverse tangent of both sides. So your theta here will be arctan of x over 4. All right. Now, I don't know, but some also accept this answer. Instead of computing exactly what sine theta is, they already know that theta is arctan of x over 4. So what others do is at this point, they'll just replace all thetas by arctan x over 4. So what they'll have is sine of arcsine of x over 4 plus the constant c, right? Which for me is also acceptable. It's just that this doesn't look as elegant as this one. So because this, so no, not arcsine, arctan. Right, because theta is arctan. They simply replace the theta here that they see inside the sine by the arctan, right? But this is not as elegant as this answer here. So yeah, but for me, this is also acceptable. All right. Okay, and yeah, let's see the other question. Okay, Fatuma has another question. How about the others? Any particular problem in mind for the coverage of the test? Or do you guys really feel prepared for the exam? Oh, before I start problem 6, some of my students from the other lab or earlier this morning, they asked me about certain problems that still trig sub, but they ended up with integrating cosecant cube of theta d theta. I know that some of you mentioned that you were told you can memorize the integral for secant cube theta, right? So they did that, but they got stuck with evaluating cosecant cube because they didn't memorize the integral for cosecant cube. There is a formula for cosecant cube derived in the same way as how secant cube theta was derived. Okay, but you can memorize that. But if you cannot memorize that, then you can do integration by parts here. So this would be your u, this would be your dv. Okay, but that will take you a couple 2 or 3 minutes at least to solve this using IBP. So if you can memorize the integral for cosecant cube, then go ahead. Also for cosecant, for integral of cosecant theta, d theta, and cotangent theta, d theta, you might as well try to look for the formulas for this. You can memorize them or know how to derive them. Simple u substitution for cotangent, a little bit of a trick needed for the integral of cosecant theta. But if you memorize secant theta and tangent theta, then might as well also memorize the formulas for the integral of cosecant and cotangent. It's just that we didn't use them in the class in so much as we did for secant and tangents, but you don't know and try to rattle you with having to work with cosecant and cotangent. But the process is the same as secants and tangents, but it wouldn't hurt if you can memorize the formulas for their integrals. Okay. Now going back to this question, u substitution, can it work? You can let u be equal to 1 minus x. Yeah, I guess we can make u substitution work here, but since we are in chapter 8, probably you want to solve this via trigonometric substitution, okay? And that's possible because you have a radical, and the radical is the form a squared minus x squared. So here we will let x to be equal to sine theta. So dx will become cosine theta d theta, right? Then do the substitution. So we'll have sine cubed theta times square root of 1 minus sine squared theta. And then dx is cosine theta d theta, right? So we'll have sine cubed theta. And then this guy is cosine squared. And then the square root of cosine squared is just cosine. And then the cosine theta coming from the du. Okay. Now essentially, what we have here is sine cubed theta times cosine squared theta d theta, which is a combination of powers of trig functions. So this is something from section 8.2, I think. So for this problem, we have an odd power for sine. So remember, if you are dealing with powers of sines and cosines and you see an odd power of one of those trig functions, you isolate that odd power and reserve that for the du. Again, I am reserving this for du. So you do that for whatever has the odd power. Since here the odd power belongs to sine, isolate one of the sines so that you have both even powers there. And keep in mind that we are reserving that odd power, that lone power, as the du. So if this is the du, then we are targeting u to be cosine theta, right? So everything else aside from this guy should be written in terms of cosine. And that's why we are happy to have just even powers here. Because you have even powers, so you can write it in terms of, or using the Pythagorean identity. So sine squared is 1 minus cosine squared. Cosine squared theta here. And then you have sine theta, d theta here. Then you can proceed with the u substitution. We'll let u be equal to cosine theta as what we planned, because we want du to be negative sine theta d theta. So I'm missing a minus sign, so let me just apply that outside. So this would be 1 minus u squared times u squared times du. So expand the product, so I'll have u squared minus u to the fourth du. Oops. Then integrate term by term, so I'll have minus u cubed all over 3 minus u to the fifth all over 5 plus the arbitrary constant c. You can rewrite it as u to the fifth over 5 minus u cubed over 3 plus the arbitrary constant c. And then we revert to the original variable u, to the variable theta rather. So u is cosine theta. So we'll have cosine to the fifth theta all over 5 minus cosine cubed theta all over 3 plus c. All right. But we're not done yet because the original problem was given in terms of the variable x. So we need to draw a triangle here. Recall that we let x be equal to sine theta. And then I can think of it as x over 1 because sine is opposite over hypotenuse. So if I draw a triangle here, I'll assume that the right angle is here. Theta is there, right? Opposite theta should be x units. So opposite theta, that's there. So it's going to be x units. Then the hypotenuse is 1. So the third leg via the Pythagorean theorem is root of 1 minus x squared, which I know makes sense because this is the one that gave us problems in the original integral, right? So it seems that we have the right triangle here. But remember, we're looking for cosine theta because the answer we have right now is in terms of cosine. So looking at the triangle, cosine is adjacent over hypotenuse. So it's going to be root of 1 minus x squared all over 1. Or actually, you could have used the Pythagorean identity right away here. So you actually don't need to draw the triangle. But anyway, you'll get the same answers. So the final answer here would be 1/5 cosine theta, which is root of 1 minus x squared raised to the fifth minus a third of 1 minus x squared raised to the third power plus the arbitrary constant c. Okay, does that make sense?
Yeah, I was looking at my work. I just messed up like writing, like when I was writing down my equations. I just
I see. And that's how you got a complicated trig function as your simplified integrand? Yeah, sort of some exam mentality since this was given as a problem in the exam. And if you run into a very complicated trig function that cannot be solved, then it would be good to check your steps, retrace your solution. Probably you just mess up one of the powers and so on. That's why it didn't turn out to be a nice integral and so on. So this was if this was given an exam, then the professors probably have solved this beforehand and saw that, oh, this is solvable. So they will give it to you. So that's an indication that if you get an extra difficult form, then probably you committed a mistake somewhere in the middle of your solution. So it would be good to retrace your steps. And retracing your steps is much easier if you included a lot of details in your solution. So that's another advantage of including everything in your solution. Okay. Okay, I think that answers all of the questions that were sent so far. Anyone else who have a question? No questions? Sure. We still have 19 minutes in the class, so if you don't have any more questions with this, probably we can start looking at some examples from section 9.1. Or you want to talk more about the exam?
Sorry, just to input, like, I know there's one FRQ on the test. Do you think it's going to be like, what do you think the FRQ is going to be if you They're just yeah.
Yeah,
Well,
as
not
much
fake.
as as much as possible, I hate to speculate. I don't want to give you false hopes. But did they mention that there's only one FRQ?
Yes.
But I'm thinking that will have several parts. Yeah. If I am to write the exam, probably I'll put a trigonometric substitution problem. Because you see, if I have a trig substitution with 4 parts, okay, one question with 4 parts. And I think those 4 parts will entail uh, integration problems that will require you to use one of the methods. Probably you'll do partial fraction decomposition, but I'm hoping they won't make it very hard. I mean, only with linear factors in the denominator, at most one repeated linear factor, then another linear factor, because I don't think they will give you very complicated partial fraction decomposition, because solving for the constants on the numerator of the partial fractions takes a lot of time, and that's algebra. I don't think they will. They want you to focus on the algebra steps. Power sub trig functions might be also there, integration by parts, and trigonometric substitution. But inside trigonometric substitution, you might need to use U substitution and so on. So yeah, but if it's one FRQ with 4 parts, I don't think they will give you very complicated integrals to evaluate. Probably not a hybrid between 2 methods, except possibly for trigonometric substitution. Okay?
Thank you.
But that's just me. Don't rely on that. That's my opinion. And I am not involved in drafting the test, so I don't have any idea at all. Okay, let me see. Okay, should we do sequences? Okay, so you have sequences. Well, I'm not sure what you already covered, but sequences are nothing more, but these are still functions. So these are functions like your usual x squared, ln of x, e to the x, but the difference is their domain is just the set of natural numbers, right? Natural numbers, 1, 2, 3, and so on. So that's why some people say sequences is just an ordered list. Oops. Of numbers. Because a main difference with the usual functions that we had been working on since Cal 1 is that we cannot list all the elements of our functions. Because say for y equals x squared, x will take infinitely many values, right? So, and then there's no way we can write all of those values. But that's a bit different for sequences, because for sequences, the domain is just a set of natural numbers. So though the set of natural numbers is still infinite, there's it is discrete in the sense that there is a gap between 2 natural numbers. So we can list them into we can put them into a list. So for instance, this is a sequence 1, 4, 9, 16, 25, and so on. This is a sequence, right? Because this is a function whose domain is a set of natural numbers. You can take this to be f of 1. This is f of 2. This is f of 3. This is f of 4. This is f of 5, and so on. So if you will sketch the graph of this sequence, this will be a disconnected graph, or will just be a bunch of dots, because the domain is simply the set of natural numbers. So for instance, function value at 1 is 1. There goes a point. When x is equal to 2, function value is 4. So you got that. and then 3, we get 9, and so on. Okay, you cannot connect the dots like what we did for functions. Like maybe here you know that, oh, this represents x squared. But if you draw the graph of x squared, it would be a parabola, right? But you cannot do that for sequences, because once you connect them via a curve, that means here 0.5 will have a function value, but 0.5 is not in the domain of our sequence, because sequences only take as an input natural numbers. So there is no function value corresponding to 0.5. There's no function value corresponding to 5/2 and so on. Only whole numbers, or in particular, only natural numbers has function values. So, okay. So if you are asked to sketch the graph of a sequence, do not connect the dots, because that would be wrong, because you are drawing a function whose domain extends beyond the set of natural numbers. Okay, so there are several ways of writing sequences. The first one is this, which is as an ordered list of elements in the sequence. And I would like to emphasize the term ordered. And that's why it's called sequences, because there's an ordering between the elements. So the sequence, say 4, 1, 9, 16, 25, and so on, is different from this sequence. They are not equal to each other, okay? Because a sequence is an ordered list. So even though they appear to have all the same elements, but one goes first here, then 4, but here 4 goes first, then 1, that makes these two sequences not equal to each other. Precisely because 4 is the function value for 1, 1 is the function value for 2, and you see now the difference. F of 1 in the red sequence is 4, but in the black sequence, f of 1 is equal to 1. And then f of 2 here is 1, here f of 2 is 4. So these two guys are different sequences, okay, because ordering matters. And hence, that's why we call them sequences. Another way of writing sequences is via formula. So you can just simply enclose n squared inside braces, right? So this tells us that to get the listing of elements of this sequence, all you need to do is to plug in natural numbers starting from 1, then 2, then 3, and so on. Again, ordering matters. So you plug in 1, we get 1, and then plug in 2, so we get 4, we get 9, 16, 25, and so on. And this is the black sequence we wrote earlier, okay? Another way of writing sequences is via a recurrence relation. I mean, you can say, okay, let me just put bullets in our examples. Another example would be the sequence AN, where A1 is equal to say 0, A2 is equal to 1, and A3 is equal to A1 plus A2. Okay. So if you want to get the list of elements of this sequence A sub n, so what is A1? A1, according to the definition, is 0. And then A2 would be, according to the definition, that's 1. But we need A3, but how will A3 look like? Well, sorry, this should be AN minus 1, AN minus 2, when n is greater than or equal to 3. Okay, so here, since we are looking for A3, and this formula tells us how to compute it whenever n is greater than or equal to 3, so we plug in here. So this tells us that A3 is equal to A2 plus A1, right? I simply replace all n's by 3. And so this would be the sum of the first two. So this would be 1 again. And then how do we get A4? A4, according to this formula, is A3 plus A2. So basically, it's the sum of the two previous terms. So we'll get 2. And then what do you think would be the next element in the sequence? Anybody? Are you guys still there? I probably think the question is too easy. That's why nobody's trying to answer. But you'll get 3, then 5, then 8, then 13, 21, and so on, right? So this is a sequence comprised of elements which are sums of the previous two elements. Okay. So what are things we can do about sequences? Well, we can look at several properties of sequences. For instance, the first set of exercises ask us to find the least upper bound if it exists and the greatest lower bound if it exists. Well, as the name implies, the least upper bound is the smallest number that is greater than everything in the set, while the greatest lower bound is the largest number that is smaller than everything in the set. So graphically, if your set is over here, okay, if this is your set S, okay, now everything in here, everything to the left, these are lower bounds. Because the numbers to the left of this line here is smaller than everything in the set. Now, on the other hand, everything here to the right of the set are upper bounds. Oops. Because all numbers in the green portion are larger than everything inside the set S. Okay, so those are lower and upper bounds. And then how do we get the least upper bound and the greatest lower bound? Well, as the name implies, you'll just take what is the maximum value over here and what is the minimum value over here. So if we're looking at the figure here, this line looks like to be our greatest lower bound, or GLB. And this number here looks like to be our LUB, or the least upper bound. Okay. So let's see in this example, So first one, what do you think is the LUB? And what's the GLB? Okay, let's start with the LUB first. What's the LUB for problem 1? Really, guys? Nobody wants to answer?
Is it 2?
That's right. No. What am I asking for? GLB or LUB? I forgot. What's the LUB? What do you think is the LUB? The least upper bound. Actually, for this problem, the least upper bound is, yes, go ahead. Any guess?
Is it 5?
Right. The least upper bound is 5. Because what are the upper bounds? So can you give me upper bounds for this set? So when I say upper bound, a number that is greater than everything inside the set. So you can give 6, you can give 10, you can get 1,000,000. But to get the least upper bound, you should get an upper bound that is smallest among the upper bounds. So the answer is 5. The GLB here would be 2, right? Because that's the smallest, that's the largest lower bound. Okay. Let's see. How about problem 4? LUB and GLB. Least upper bound would be 4. Oh, sorry. Yeah, I thought nobody wants to answer. And the GLB is what?
Would there be any, or is it still considered negative infinity?
Well, the thing is, you're on the right track, but negative infinity is not the number. So you say, okay, there is no greatest lower bound. because it spans from the left end of the real number line. So we cannot get the end of that. So yeah, if you look at the graph of this interval, it's going to be like this. So 4 here. So that means this will cover everything towards the left. And remember that the lower bound is, oops. And you know that the greatest lower bound should be a boundary on the left, but the left is unbounded, so there would be no greatest lower bound. Okay, how about, let's see. How about problem 9? LUB and then GLB. What's the least upper bound?
There would be none.
Nope, try again. Maybe you can start by thinking, what are examples of upper bounds? So when you say upper bounds, those are numbers that are larger than everything in this set. So can you give me one example?
2.
Right, 2. So if you have an upper bound, I think there's a theorem in the lecture that says if you have an upper bound, then there should be a least upper bound. That's basically the completeness property of the set of real numbers. So since you were able to give me an upper bound, which is 2, you're correct, then there must be a least upper bound according to that theorem. So what is the smallest number that is larger than everything inside the set? Of course, 2 cannot be the least upper bound because I can think of an upper bound that is smaller than 2, say 1.5. 1.5 is an upper bound because it is larger than everything in the set. But, oh yeah, that's an upper bound, and that is smaller than 2. So that means 2 cannot be a least upper bound. So can you think of another upper bound that is smaller than 1.5?
Would it be 1?
Yes, 1 is an upper bound. But is that the smallest? Yes, actually. Because if you go smaller than 1, then that is not an upper bound anymore because 1 is included in the set. And probably that's what confused you because upper bounds or least upper bounds and greatest lower bounds can be inside a set. Okay. How about the greatest lower bound? Will this set have a greatest lower bound? Okay, first thing, can you give me a lower bound for this set or for that sequence? Can you give me a number that is smaller than everything inside a set? We're talking about set 9. Can you think of a number that is smaller than everything in the set? So the set goes 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on. So can you give me a lower bound? Something that is smaller than everything in the set? Yeah, Fatuma, you're right. 0 is a lower bound. -1 is also a lower bound. -7 is also a lower bound. And since we know that there exist lower bounds, then automatically there is a greatest lower bound. So, well, -infinity is technically not a number, so it is not a lower bound, at least for our context. If you go to higher math, people accept -infinity as a number, but for us, we stick to the real numbers, so -infinity is not considered a number. So it's not a lower bound, but you're right, you already gave me a lower bound. So since you were able to give me a lower bound, there should be a greatest lower bound. And what do you think is the greatest lower bound? Greatest lower bound is going to be 0, right? Because 0 is a lower bound, okay? But if you go higher than 0, that will not be a lower bound anymore, okay? Because what you see here, the pattern is it gets smaller and smaller. So if you say 0.1, definitely it's not a lower bound because 1 over 11 is inside the set, and 1 over 11 is smaller than 0.1. So 0.1 is not a lower bound. And if you go a little bit to the right of 0, that will not qualify as a lower bound either, because the pattern, this pattern goes on forever. So I mean, if you sketch the graph, you start at 1, and then you get 1/2. Say 1/2 is here, then you go 1/4, and then you go, oh, what am I doing? So 1/2 is here, you go 1/4, you go 1/5, you go 1/6, you go 1/7, and so on, but you will not get past 0. But nothing, there's no lower bound greater than 0, okay? All right, so let's go back to this on Monday. So we'll answer some of the other interesting problems over this worksheet. I already uploaded this blank worksheet, I think 14. But yeah, let's stop here, unless you have some clarificatory questions. So probably on Monday you'll be able to participate more in the discussions because the exam is already done. So let me know how the exam went, and then let's start with the chapter 9 again on Monday. All right, guys. Good luck on the test. Have a good day, and yeah, see you again on Monday. Bye, everyone.